Let's consider this following random potential shown here in black and ask the following simple question. Imagine we have an incoming wave. Will this wave be transmitted or will it be reflected? We can now take a similar random potential but simply smoother and ask the same question. Will it be transmitted? And if it's fully transmitted, we have a delocalized system. Well, if it's fully reflected, we have a localized system. Or we can take even a smoother potential and ask the same questions. So if we take a look at these three potentials, it turns out that the one in the middle, the one with the average correlation length or smoothness, will be the most reflected. And this is one of the questions we're looking at in our paper with Hikem Elush and myself, Michael Hilke. And the idea is to look at localization, which is not only happening for electromagnetic waves or mechanical waves, but it can also happen in quantum particles, such as atoms, electrons or photons, and even in time-dependent fluctuations. The general idea is to look at a wave equation where psi of x is the amplitude, while p of x depends on energy and the random potential and is simply the classical momentum. In quasi-one dimensions, we can consider a potential which depends only on x, and which is characterized by some correlation length L, which is the smoothness of that potential. For a small correlation length, it will be rough, and in average or medium correlation lengths, it will look smoother, and for large correlation lengths, we have something quite smooth. In all these cases, we have a transmission which will decay exponentially with distance x, and the decay rate lambda is what we call the Lyapunov exponent. If we plot this decay rate, or lambda, as a function of correlation lengths, we see that for an intermediate correlation length, we have the maximum decay rate, or maximum Lyapunov exponent lambda. At high correlation lengths, we see that there's a discrepancy between the exact numerical calculation, which is in blue, and the Born approximation shown in red. So, to understand this behavior for the entire disorder range, we developed a new technique which allows us to calculate this Lyapunov exponent. And instead of looking at the wave equation directly, we look at the wave equation where we add a small nonlinear term which depends on the difference between the classical momentum and the quantum momentum minus I dx. The solution of that is explicit, and we can then disorder average that solution, in which case we find an expression of the Lyapunov exponent in terms of a correlation function Cp of x shown here. And this is really the main analytical result of this paper, which is deriving this new expression for the Lyapunov exponent. To convince you that indeed this Lyapunov exponent is correct and describes the localization behavior for all disorder, we plot here the Lyapunov exponent as a function of disorder strengths, and the blue dots is our nonlinear approach, while the blue line is the numerics, and we see that the two match perfectly, while the red line, which is the Born approximation, does not fit. The same is true if we plot this Lyapunov exponent as a function of correlation lengths. We see again that the numerics and the nonlinear approach match perfectly, while the Born approximation does not. So to conclude, we have found a new way to calculate the Lyapunov exponent expressed in terms of a correlation function Cp, and this result has important implications for many systems with strong disorder, such as waves, quantum particles, and time-dependent fluctuations. And with this, I would like to thank you for listening to this abstract.